Hello, students. Today we're going to be working on our final unit of calculus, and this unit is what I consider to be more for the engineers in the group. So today we're going to start off just by looking at the area of a region between two curves. And hopefully you've gathered by now that integration is showing you the area from a beginning point to an ending point under the curve, between the curve and the x-axis. And if it's above the curve, then it's a positive area. If it's above the x-axis, it's a positive area. If it's below the x-axis, it's a negative area. So today we're going to look at the area between two curves, such as what you see on the screen right here. And so what we're interested in is this shaded region that we would have between my blue line and my red parabola. So this area that I'm coloring in right here. And so what we're going to need to do is to find our beginning and ending points, and we'll do that by finding their points of intersection. Now, you can probably see those points of intersection by looking at your graph, and if I use Desmos, of course, that would show up as -2, 0, and as 1, 3. So my x values would be -2 and +1 that are setting my boundaries for this area between the two curves. Now I'm going to show you the notes that go with this, and they state that if you have continuous graphs, that the area between the two curves can be found by doing the integral from a to b of the top curve, which I'll call f of x, minus the bottom curve, which I will call g of x. So it's very simple. You'll take the two curves and subtract them and integrate from a to b. You can also have curves that are not functions that are defined by y equals. And if that is the case, then instead of going top to bottom, you will subtract right curve minus left curve. And you'll integrate along boundaries established on the y-axis as opposed to the x-axis. So I will go through. All right, so our first example you see here on the screen, we're finding the area between y equals x squared plus 2x and y equals x plus 2. And you might see those, one of them as f of x and the other as g of x. And you just need to pay attention to the graphs and which curve visually is above the other curve. So in our case, the line y equals x plus 2 is above the parabola y equals x squared plus 2x. So to find the area between, I've already highlighted on the screen for you the points of intersection, but I do want you to realize that you could do some algebra to find those points of intersection. You could set x squared plus 2x equal to x plus 2. This would be the case of if for some reason you didn't have access to a calculator. This would be another way to find those points of intersection. So since it's a quadratic, we would have to get one side equal to 0 and then factor and set each one of those factors equal to 0, and you would find that indeed you do get the 2 points of intersection at x equals -2 and x equals 1. So then we will find the area between the two graphs by doing the integral from our leftmost point of intersection, so the x, -2, and our rightmost point of intersection, 1. We're always using the x values on these. And then we'll do the top curve, which is x plus 2, and subtract from that the bottom curve, which is the parabola x squared plus 2x. And then before integrating, probably would want to combine like terms. So the integral from -2 to 1, we would have negative x to the second, and then minus x, if we distribute our subtraction sign, and plus 2 dx. Now we'll use our power rule and do the integration. So now we have area equaling negative x to the third over 3 minus x squared over 2 plus 2x. We're evaluating that from -2 to 1. And now you'll need to plug in your values. So remember, we do the top one first. So we'll have -1 to the third over 3 minus 1 squared over 2 plus 2 times 1 minus, and then we'll be substituting in the -2. So it's the negative of -2 to the third over 3 minus -2 squared over 2 and plus 2 times -2. And combining like terms and getting the fractions with common denominators, you should end up with an answer of 9/2 or 4.5. And that would be the area that you see shaded in yellow between those two graphs, the y equals x plus 2 and the y equals x squared plus 2x. All right, our second example, we have functions that are f of y and g of y. We're not as familiar with those. Whenever you have that type of function, you can think of that as x equals. And so x equals, particularly in the second case, x equals 0 is the green line, which is the y-axis. So for this, we're going to need to find our points of intersection. We're just going to use the graph to find those. And so we've got 0, 0, because we have our boundary here between these two curves. They intersect at 0, 0. And then we also were given an additional boundary of y equals 3. So we're going to find where our curve, our red curve, intersects with the horizontal line y equals 3. And so to do this integration, we have a curve that is to the right of this y-axis boundary. And so we're going to integrate from right to left. And so we'll use the y's as our limits of integration. Our area will be found by doing the integral from 0 to 3, again using the y's. we'll have our right curve, which is f of y. That's going to be y over the square root of 16 minus y squared, minus our left curve, which is 0. And then this is in terms of y, so we'll have dy. So for this problem, we're going to need to use a u, and in doing that, our u will equal the denominator without the square root. Our du will be negative 2y dy. And so as we get this set up, we'll need to put a negative 2 here and a negative 1/2 on the outside so that we get our negative 2y dy. So this is going to become negative 1/2 times the integral. And we're going to have 1 over the square root of u. So we could write that as u to the negative 1/2 du. And I'm going to adjust our limits of integration. So when u equals 0, when y equals 0, then u will equal 16 minus 0 squared. So 16. That'll be our lower limit of integration. And then when y equals 3, then u would equal 16 minus 3 squared, 16 minus 9 making 7. So our upper limit of integration would be 7. So now we are ready to integrate, and that's going to give us an area, negative 1/2, and then we'll do the power rule. U to the negative 1/2 plus 1 would make u to the 1/2 over 1/2. And I'm just going to rewrite that as 2 times the square root of u. We're going to evaluate that from 16 to 7. And so as we continue on with our evaluation of the area, I'm going to move to the top of the screen. Then area would equal negative 1/2 times 2 times the square root of 7 minus 2 times the square root of 16. And we'll just get a decimal approximation for this. Your decimal approximation, 1.354. 1.354. All right, our third example, I've gone ahead and graphed, and it looks like we have more restrictions this time, more boundaries. So we're looking at y equals 4 over x, and that's this hyperbola that you see here. You have x equals 0, that's the y-axis, y equals 1, a horizontal line, and y equals 4, another horizontal line. So at first thought, since this is y equals, you might be thinking that we would do top to bottom, but that's not going to allow us to really involve this boundary for the y-axis. So instead, we're going to need to look at this from the right to the left, and we're really looking at where we have an intersection point right here at 1, 4, where we have an intersection right here at 4, 1. We're actually going to be using the y's as our boundary. We'll be looking at this as a right curve minus the left, which again would be the y-axis. So the first thing I'm going to have to do is take my equation y equals 4 over x and solve it so that it's y equals. So I can quickly multiply both sides by x and then divide by the y so that I get x equals. It would be the exact same graph, but now we've got it in terms of x equals. So again, we're going to do our area, and we will be integrating using the y values from 1 to 4, and we will do the right curve, which is 4 over y, minus the left one, which is the y-axis, or 0. So we're integrating 4 over y dy. All right, well, so that would be a natural log. I'll go ahead and rewrite that. So the integral 1 to 4, 4 over y dy. And so we can integrate that, giving us the area equals. Now, you might want to put the 4 on the outside and then do the natural log of y. And then, and that y would need to be an absolute value. We'll evaluate this from 1 to 4. So we'll substitute in. This will be 4 times the natural log of, and now you don't really need the absolute value because you're putting 4 in, which is positive, minus, and then 4 times the natural log of 1. And depending on what kind of answer is required, this would be 4 times the natural log of 4 minus, and then the natural log of 1 is 0. And so that's 4 times 0. So this is just minus 0. So if you need an exact answer, 4 natural log of 4, or a decimal approximation, which would be approximately 5.545. So the area in this shaded region is 5.545. All right, for our fourth and final example, we're going to look at 2 curves. One of them is an x to the 4th curve, so you can see that one's in pink. It makes a W shape. And then our x to the 2nd curve, which is in blue, it's a parabola shape. I'm going to go ahead and look for those points of intersection. You could get those points by setting the 2 equations equal to each other and solving algebraically, or we could get them using our graph. So I want you to notice a couple of things. First of all, as we look at this blue graph, which is the parabola, you'll notice that the blue graph is the top graph and the pink graph is the bottom. But then it switches as we move into this area. The pink graph, which is the W shape, is the top graph, and then it switches back. So we're going to have to split this up. The other thing I want you to know is that this graph is symmetrical. So it would be much easier to just do half of the problem, the part from the y-axis over, and then double our area. So I'm actually just going to concentrate on this point of intersection, this one, and this one. And so our integration is going to look like this. We'll have the area equaling. And so for our first part, we will begin. Now remember, we're only going to do half of it, and then we're going to double our answer. In fact, I'm going to put a 2 in a big bracket there so we remember it. So we're going to go from 0 to our x point of intersection. So that would be at 1. So 0 to 1. And our top graph in that case is the W shape. So that would be the x to the 4th minus 4x to the 2nd. We're going to subtract from that then the x squared minus 4, the parabola. But then we've got to add to this. So now we're adding to that the next part of our graph. So a new integral. And in this integral, which is going to go from 1 to 2, so we're picking up the rest of the graph. Now the parabola is the top graph. And so we'll integrate x squared minus 4 and subtract from that. So top minus bottom, x to the 4th minus 4x squared dx. Okay, so there's our setup. And again, all of this then has to be multiplied by 2. All right, so we'll have our area equaling 2 times our integral from 0 to 1. And we've got some like terms we can combine. So we'll have x to the 4th minus 5x to the 2nd, and then plus 4 dx. We'll have to add to that our integral from 1 to 2. And when we do this combination, then we'll have negative x to the 4th. We'll have positive 5x to the 2nd, and then minus 4 dx. Now, it looks like I'm going to be running out of time. You might be able to go ahead and finish this integral. I'm going to tell you what your final answer is. It should be a equals 8. I will make one more video and go through the rest of the problem. All right, so this is just the integration part of the last problem when I ran out of time. So we'll integrate that first part, making x to the 5th over 5 minus 5x to the 3rd over 3, and then plus 4x. We'll be evaluating this section from 0 to 1, and then integrating that next portion. We'll have negative x to the 5th over 5 plus 5x to the 3rd over 3, and then minus 4x. And again, evaluating this part from 1 to 2. So as you can see, it's nice to at least be able to do half the problem and then double it. All right, so, and I actually believe that I need another bracket around all of this because all of that is doubled. So now the area is going to equal 2 times, and now you have to start plugging in your values. So you'll have 1 to the 5th over 5. So that's going to be 1/5 minus, then you'll have 5 times 1 to the 3rd. So that's going to be 5 over 3 plus, and then 4 times 1, which is 4, minus, and fortunately putting 0 in for all of those is just going to be 0. So I'm going to leave that as that. Then we'll have to add Now we're going to put 2 in for all of our x's. So we'll have negative 2 to the 5th over 5. So that will be negative 32 fifths, plus we'll have 5 times 2 to the 3rd. So 2 to the 3rd is 8. 8 times 5 is 40. So we'll have 40 over 3 minus, and then we'll have 4 times 2. That's 8. And then we get to subtract from that. So we've got kind of a parentheses nightmare here. So now we're going to subtract from that, plugging in 1. We'll have negative 1 to the 5th. That'd be still negative 1 over 5. Plus, we'll have 5 times 1 to the 3rd. So 5 over 3. And minus 4 times 1. And remember that everything then is doubled. So I'm going to let you go through all the math on that. You can go through and combine your like terms, and you can add up your fractions using your common denominator. You will need to remember that your final answer multiplies by 2. Whatever you get inside that bracket, multiplies by 2. And so you should get 8 as the area between those two curves.